99% of developers don't understand one of the most fundamental aspects of computing, system calls. Think about it. Every time your application opens a file, allocates memory, or sends data over the network, it has to ask the operating system for permission. But how does this actually work? Here's the thing. Understanding system calls isn't just a theoretical exercise. If you don't know what's happening under the hood, you're leaving performance, debugging, and security on the table. In this video, we're breaking down what system calls are, how they work, and why mastering them can take your software engineering skills to the next level. By the end, you'll know something most developers overlook entirely. Let's dive in. System calls are mechanisms that allow user space applications to request services from the operating system kernel, like accessing hardware or managing resources. Why is this necessary? Well, modern operating systems separate the execution environment into user mode and kernel mode. User mode is where your application runs. It's a restricted environment to protect the system from crashes or malicious code. Kernel mode is where the operating system has unrestricted access to the hardware and can execute privileged instructions. Direct access to hardware is not allowed in user mode. Instead, your app has to ask the kernel for help. Your application is sandboxed in user mode for safety, and system calls act as a bridge between user space and kernel space. To perform tasks like reading files, allocating memory, or communicating with other devices, your app has to make a request to the kernel, and that request is called a system call. Now let's look at the workflow of a system call. It all starts with a user space API call, when your application calls a library function like read or write. These functions are part of standard libraries like glibc that provides an abstraction or wrapper for system calls. The library function triggers a trap instruction which switches the CPU from user mode to kernel mode by flipping the mode bit in the CPU. Why is this switch necessary? Because only the kernel can execute privileged instructions like accessing hardware or managing memory. Along with the trap, the application passes a system call number and arguments via registers or the stack to tell the kernel what it needs to do. Next, we have the kernel handler. The kernel looks up the system call number in a system call table and executes the corresponding handler. For example, if you're reading a file, the kernel interacts with the file system to retrieve the requested data. Once the task is complete, the kernel flips the mode bit back to user mode using a return from interrupt instruction and passes the result back to the application. So now we are back in user mode. This process is what makes system calls secure and reliable. The kernel acts as the gatekeeper, ensuring that no application can bypass safety measures or access resources it shouldn't. Okay, now that we understand the workflow, let's take a step back. What are the actual use cases of system calls? And the short answer is pretty much any time your app interacts with hardware or system resources. First, we have file management. Calls like open, read, and write let your app interact with the file system. For example, when you open a file, the kernel checks if you have permission and locates the file on disk. The second use case is process management. System calls like fork create a new process by duplicating the current one, while exec replaces a process's memory with a new program. These are critical for tasks like launching new applications or running scripts. Third, we have memory management. Calls like mmap let your app request memory from the kernel. The memory is mapped to physical pages and the kernel ensures efficient and secure access. Fourth, we have networking. Creating a socket with socket and sending data with send involves system calls. The kernel handles protocols, port management, and device communication. And finally, we have device I/O. If you want to read from a keyboard or write to a display, system calls like I/O control manage the communication between your app and hardware drivers. The TLDR here is that system calls abstract away the complexity of dealing directly with hardware and allows developers to focus on higher level logic while the kernel ensures safety and consistency. Now, why should you even care about system calls? There's three critical reasons. In terms of performance optimization, every system call involves a context switch between user mode and kernel mode, which is expensive. By understanding this, you can optimize your code, for example, batching I/O operations instead of making frequent small requests. And in terms of debugging, tools like strace let you monitor system calls in real time, showing you exactly what your application is asking the kernel to do. This can help identify permission issues, I/O bottlenecks, or unexpected behavior. And in terms of security, system calls are a common attack vector. If your app doesn't properly validate inputs before making a system call, it could expose vulnerabilities like buffer overflows or privilege escalation. Knowing how system calls work allows you to write better performing, more secure, and easier to debug applications. System calls are the unseen backbone of your applications. Every time you write code that interacts with the outside world, you're relying on this powerful mechanism.